So CDO is equal to 1 minus US divided by UE to the cube times 0.09. So 0.09 square if the square is correct, and times pi square divided by 16. All right. So that's my CDO, and also initialize this at CDO. So let's take another figure, and CDI and CDO. I think I also need to reshape them. CDI, and CDO. Let's run it. Okay, so figure 3. Oh, I forgot to hold on because I have two figures. One is CDO, one CDI. And let's make the CDO to be a mesh instead. Okay, so this is what they look like. The surface is the inner layer dissipation, and the mesh is the transparent mesh. It's okay. So what you can see is the mesh is the one where the color is on the lines, and the surface is the one where the lines are black and the colors in the squares. So the one that has colors in the squares is my surface, that's CDI, and the CDO is the mesh with the white surfaces and colored lines. So what you see is that first of all, there is some effect of Reynolds-Steinberg, especially for CDI, right? So for the inner dissipation, the lower the Reynolds-Steinberg is, the more the dissipation is, right? Because lower Reynolds-Steinberg, there is more dissipation in the inner layer. And also the trend with respect to H is opposite. So for a lower H, when you have a very energetic boundary layer, a lot of the dissipation is in the inner layer, right? And when you have a boundary layer that has a higher H or closer to separation, remember the inner layer becomes smaller and smaller. So when you have a turbulent boundary layer almost at separation, the inner layer becomes 0 because there is no skin friction coefficient, right? So the dissipation of the inner layer as you approach its separation basically becomes 0, right? So we didn't get to the point, but like when you are close to separation, the inner layer has no dissipation, and all the dissipation comes from the outer layer. All right, and if you look at the total dissipation, when you have a separating or separated turbulent boundary layer, the total dissipation is actually higher. You get a lot of dissipation through the turbulence. All right, so this is how we get the correlations between the different boundary layer thickness and the closure terms we needed to integrate the